Hi guys, welcome back to Calculus. Chapter 4.3 deals with vertical and horizontal asymptotes, which we've seen before, but we're going to revisit them. And this was a lesson that I missed because I missed those last 2 days of March, just before March break. I was in quarantine. So fortunately nothing happened, but that's why I wasn't at school. So what I want to say to you is that we have to do this unit to catch up to the other class. So I'm going to try and do it as efficiently as possible here. What I want to tell you is that we're going to revisit asymptotes and tell you that the true understanding of asymptotes, the real mathematical understanding of asymptotes, actually comes once you've learned limits. So we're going to revisit an old topic, but looking at it from a slightly new angle. If you look at the picture of a vertical asymptote, you can tell that the limit as x approaches 4, and this plus sign, of course, remember, means from the right side. And so that would be from this side. And as the function gets closer and closer towards this asymptote, of course, it shoots to infinity. So you can write the limit is positive infinity. You can also write does not exist. Different textbooks have different approaches. If you do the limit as x goes to 4 on the left side, meaning approach 4 but come at it from the left, it shoots down to negative infinity. Basically, the limit doesn't exist. And the fact of the matter is that that's really what a vertical asymptote is. If you have a limit as x approaches a certain number and that limit doesn't exist, you have a vertical asymptote there. Now, for example, if you had some function, I don't even know what the function is, but I'm saying that the limit as x approaches 3 of this function doesn't exist. Given, it's a fact. The limit as x approaches 3 doesn't exist. What that means is that guaranteed when you eventually graph g of x, you will have a vertical asymptote at x equals 3. Now, we're used to thinking of vertical asymptotes as, well, wherever the function doesn't exist, which is sort of the cheating method. It works, but it's not the real mathematical reason why they don't exist. So this statement I'll come back to in a minute, but basically if I said to you, what would be the equation of any vertical asymptote here? You wouldn't go about solving the question any differently than you had done in the past. If you see x minus 1 and you know that x equals 1 is a restricted value, then you would simply say, well, there's got to be a vertical asymptote at x equals 1. Same thing, there's going to be a vertical asymptote when x equals negative 2. That's the way you find it. That's the same way we've always found it. But as someone said, why is there a vertical asymptote? Why does it have 2 vertical asymptotes? The answer is not because x doesn't exist, but rather the limit as x approaches 1 of this function can't be calculated, because remember back in the first chapter we learned to play with the functions so that we could sub that value in. You'll never be able to do that here. And so we go, oh, okay, the limit doesn't exist. That's the real reason why there are these. If you took the limit as x approached negative 2, same thing, it doesn't exist. This is just a bit of a refresher on how you find these asymptotes. If you look at this particular graph, I wanted to remind you that x squared plus 2 never equals 0. It's impossible because this squared is positive, add a positive, never equals 0. So there's no vertical asymptote from this factor, x squared plus 2. This factor says x plus 5, of course, x equals negative 5 will be our vertical asymptote. So I'm not finding them in any other different method than we have in the past. I just provided the reason why they exist. This function says 3x plus 1 over x squared minus 3. We know that x squared minus 3 equals 0. If you solve it, you get x is plus or minus root 3. Again, I point out this example simply to remind people not to forget to do the positive and negative case. And the way we find the vertical asymptotes is we set the factor equal to 0 and solve. What causes each factor to equal 0? The x value that causes the factor to equal 0. That's where the vertical asymptote is going to be. But again, the real reason is because evaluating the limit shows that the limit just doesn't exist. Nothing really new there except for this fact. If the limit as x approaches c, meaning any number, doesn't exist, there will be a vertical asymptote at x equals that particular number. And c could be any number you want. A constant, of course, is a number. So now let's move to horizontal asymptotes. Now, we had this whole convoluted method of finding horizontal asymptotes back in grade 12. Let me remind you what those were. In grade 12, we gave you 4 different cases, and we said, take a look at your function and see which case it falls under. So for example, if the degree of the numerator is less than the degree of the denominator, we said you're going to have a horizontal asymptote at y equals 0. We didn't give a reason why. We said just believe it. We said if the degree of the numerator equals the degree of the denominator, not by more than 1, if it equals it, as it does here, second degree, then you take the coefficients of the highest degree terms and you'll have a horizontal asymptote there. Again, we didn't explain why. The third case was when the degree of the numerator is greater than the degree of the denominator. This is 4th degree, this is 2nd degree, but by more than 1. That's when you have no asymptote, nothing to worry about. But if you do have a situation where the numerator is greater by, the degree, of course, of the numerator is greater by exactly 1, you'll have an oblique. And if you remember, the way you get, the equation of this thing called an oblique asymptote, remember an oblique line is a line that is a line but not horizontal and not vertical. So it usually runs up or down. And we can find the equation of the particular oblique asymptote by doing this long division. We only do the long division to the point where there's a remainder and then you can stop. So again, x squared goes into x cubed x times. You multiply, you get x cubed minus 3x, distributive. You then subtract and you're left with 0 minus 3x, which is 3x, but x squared won't divide in. That quotient is actually the equation of your oblique asymptote. So that's a reminder of how we did it, back in grade 12. Now we're going to find the real reason you have horizontal asymptotes at these locations. The fact of the matter is, you're still going to find those asymptotes the same way you did in grade 12. You're going to look at the degrees and you're going to compare them, and you're going to use one of these 4 cases as the way to know what the horizontal asymptote is. I'm not changing the methods that you've always used. I'm only going to supply you with the mathematical reasoning of why these are true. And in order to do that, you have to take a look at these examples. So if we look at this first situation, I'm going to say, look at this function. I'm sorry that the video is not that clear. It has to do with the lighting to get my camera to work, and I'm no expert, so I'll just sketch it in quickly for you. What we see at this particular function is that we have a horizontal asymptote at y equals 5 and a vertical asymptote at x equals 4. And I call this function g of x. Now, we haven't really done much of this. We exposed you briefly to it. I mean, really briefly. So if you don't remember, don't worry, it's not your fault. But we did talk about this weird concept. What happens if x is going to, in this case, it says positive infinity. If x is going to positive infinity in this function, what I'm referring to over here, the x values go to positive infinity on the right side. On this side where the x's are negative, you go towards negative infinity the more you move to the left. So x going towards positive infinity on this function is saying, what is g doing as you move further and further and further to the right? And that's referring to this arrow, because as I go more and more and more to the right, this function actually gets closer and closer to this dotted line, which marks the horizontal asymptote. And the fact is, if you looked way out to the right, infinitely far, like when x has a value of 1,000,000, if you looked at the function that far to the right on the graph, it would actually look like it was the horizontal line y equals 5. The function would approach it and approach it and approach it to the point where you think it was sitting on top of it. And so what we say is if you're evaluating the limit as you go infinitely to the right of this function, the function approaches the value 5, where y equals 5. If you do the negative infinity, it's exactly the same idea. That means x going to negative infinity means head infinitely to the left, more and more and more and more. What is your function doing? Well, the further to the left you go, the more this function gets closer to that dotted line. So similarly, as you go infinitely to the left, the value of the function that it approaches is the value where y equals 5. And the truth of the matter is that's the definition of a horizontal asymptote. If you take the limit as x goes to infinity, and it doesn't matter if you do the right or the left or both, if one of those equals a number, c meaning a number, then guaranteed you'll have a horizontal asymptote at y equals c. Up here, the limit as x was going to infinity equaled 5. That's why we have a horizontal asymptote at y equals 5. If the limit as x went to infinity worked out to be 3, you would have a horizontal asymptote at y equals 3. So what I essentially have to show you would be, how do you know if I give you the algebra if there's a horizontal asymptote or not? Of course, you can use our techniques. This would fall into the case where the degree of the numerator equal the degree of the denominator. And so the way we know for sure there's a horizontal asymptote is because the same degree, we use the coefficients, we know for sure y equals 5. But I'm actually going to show you how to calculate the limit as x goes to infinity of this algebra. And of course, you should expect the answer 5, because we know there's a horizontal asymptote y equals 5. So the technique that I want to teach you is, how do you evaluate the limit as x goes to infinity of a function you've never seen before, to numerically see if there's an answer for it. And that's the purpose of this lesson, evaluating algebraic expressions of functions, the limits as x goes to infinity. So this is part 1 of that lesson. I'm going to stop the video now and do that part of the lesson as a separate video so that this video doesn't get to be too long. So that is the end of part 1.